magnetic resonance imaging, MRI, machines have transformed how we view and understand the human body, offering incredibly detailed cross-sectional images without the claustrophobic dread some associate with them. These machines have revolutionized medical diagnosis and treatment, allowing us to visualize organs with unprecedented clarity. Doctors can now safely locate tumors in the kidneys, brain, stomach, or pancreas and use paramagnetic contrast agents in the bloodstream to identify blockages in the heart, enabling precise, minimally invasive procedures like stent implantation. These keyhole surgeries have replaced risky open-heart operations, offering quicker recovery times. The technology behind MR seems like something out of science fiction, yet it relies on a sophisticated blend of quantum physics, superconducting magnets, computer science, and mathematics. Beneath the sleek, futuristic exterior of an MRI machine lies a marvel of engineering that most people rarely consider. Before MR, medical imaging relied on harmful ionizing X-rays or low-resolution ultrasounds. While both remain useful, they cannot match the safe millimeter-resolution images MRs provide, capable of creating 3D reconstructions of the body rather than flat 2D images all without moving parts. Imaging techniques in medicine collect signals based on the physical properties of tissues. Ultrasounds depend on how sound waves reflect off tissues of varying density, while X-rays form images based on the absorption of high-energy radio frequency waves. MRs, however, tap into something far less intuitive: the quantum properties of hydrogen atoms, which are abundant in the body's water, carbohydrates, and proteins. Specifically, MRs exploit a quantum property called spin, which makes particles like the proton in a hydrogen nucleus behave like tiny bar magnets. This spin gives each proton a magnetic north described probabilistically. Under normal conditions, the magnetic fields of many hydrogen atoms cancel each other out due to their random orientations. However, when placed in the powerful external magnetic field of an MRI, the distribution of these tiny magnets shifts, aligning more atoms with the field. This imbalance generates the signal that MR is used to create images. To produce this signal, the MRI aligns hydrogen atoms within its strong magnetic field and then delivers a precise nudge, using a magnetic radio frequency pulse. This pulse, generated by coils inside the machine that carry alternating current at a specific frequency, misaligns the hydrogen atoms' magnetic fields perpendicularly to the main field. As the atoms naturally seek to realign with the machine's magnetic field, they don't snap back instantly. Instead, they decay in a spiraling motion, creating a changing magnetic field. By placing a coil nearby, this changing field induces a measurable electric current, forming the MRI's signal. Some machines use the same coils to send pulses and receive signals, positioned close to the patient inside the MRI tube for better contrast and resolution. Others use separate coils for transmitting and receiving, allowing receiver coils to be placed even closer to the body to maximize signal strength. Increasing the external magnetic field strength aligns more hydrogen atoms, producing a stronger signal and better image quality. Common MRI fields range from 1.5 to 3 Tesla 300,000 times, stronger than Earth's magnetic field and 30,000 times stronger than a refrigerator magnet. Such intense fields can lift nearby ferromagnetic objects like wheelchairs, making safety precautions critical. For research, MRs can reach up to 20 Tesla, pushing the boundaries of imaging resolution. Achieving these magnetic fields is no small feat. Early MRs used permanent magnets limited to 0.5 Tesla, which restricted resolution. Electromagnets could generate stronger fields, but standard wires would melt under the required currents. Engineers turned to superconducting coils, a SIFA-like technology where resistance drops to zero at temperatures near absolute zero, -273 degrees Celsius. In theory, a current in a superconducting loop could flow indefinitely without a power source. In practice, this means MRI's main superconducting coil consumes no direct power, but significant energy is needed to keep it cooled. The most common superconductor, niobium-titanium, is so critical that 80% of the world's supply goes into MRI machines. Early MRIs submerged these coils in 1,000 liters of liquid helium at -269 degrees Celsius, but the helium evaporated, requiring costly refills up to $26,000 annually. Helium, a byproduct of radioactive decay trapped in underground caverns, is finite. Once released, it escapes Earth's atmosphere into space. Modern zero-boil-off MRIs use vacuum-sealed chambers and powerful refrigeration cycles to maintain liquid helium without evaporation, reducing costs and making the technology sustainable. An MRI's annual energy consumption, roughly 130,000 to 140,000 kilowatt-hours, equals that of 25 four-person households. Once hydrogen atoms are aligned and nudged, the MRI must translate their signals into images. The key is pinpointing the atoms' locations. The spiraling decay of nudged hydrogen atoms produces a signal with a unique rotational frequency, determined by the magnetic field strength 64 MHz at 1.5 Tesla, 128 MHz at 3 Tesla. By applying a magnetic field gradient using additional electromagnets called gradient coils, the machine can selectively nudge atoms in specific slices of the body. For example, a pulse at 63.998 MHz targets a slice in a weaker field, while 64.2 MHz targets one in a stronger field. This allows the MRI to image specific body sections. However, the receiver coil collects the sum of all decaying signals from a slice, so creating a 2D image requires further processing. To generate contrast between tissues, MRIs rely on two relaxation processes. T1 relaxation measures how quickly hydrogen atoms realign with the main magnetic field after a nudge. T2 relaxation accounts for interactions between hydrogen atoms, causing them to fall out of sync after the pulse. Since the coil measures the combined signal, this deficing creates a decaying T2 signal. These rates differ between tissues. Fat and water, for instance, have distinct properties. Technicians adjust two settings: the time between pulses, repetition time, and how long to wait for the signal, echo time. Rapid pulses emphasize T1 signals, highlighting fatty tissues while suppressing water-based signals. Slower pulses and longer listening times emphasize T2 signals, enhancing water-based fluids like cerebrospinal fluid. These settings, tailored to the doctor's imaging needs, allow MRIs to distinguish tissues effectively. Forming a 2D image from a slice's combined signal is complex, as the receiver coil cannot isolate individual points. Here, a mathematical breakthrough from 1822 by Joseph Fourier proves invaluable. Fourier's framework breaks down complex waves, or in this case, 2D grayscale images, into simpler components like summing musical notes to form a melody. An image can be deconstructed into weighted averages of black and white striped patterns. MRIs create these patterns physically using gradient coils to manipulate the phase of rotating hydrogen atoms. By coloring the atom's phase in grayscale white for in-sync rotation, black for 180 out-of-phase, MRIs generate striped patterns across a slice. Gradient coils along the X and Y axes control these patterns' frequency and orientation. By sampling multiple patterns, the machine builds the image through Fourier analysis, gradually reconstructing each 2D slice before moving to the next. The rapid switching of gradient coils, similar to a speaker's operation, causes the loud clunking sounds in MRIs. These machines are a testament to engineering ingenuity, combining superconducting wires, vacuum-sealed helium chambers, and precise magnetic gradients. The technology continues to evolve, with researchers pushing for stronger magnets to achieve higher resolution, while others develop smaller, cheaper MRIs for broader accessibility. This intricate interplay of quantum physics and engineering has transformed medicine, enabling non-invasive, high-resolution imaging that saves lives. The complexity of MRI technology underscores the importance of advanced diagnostic tools in engineering. Companies like Keysight provide engineers with cutting-edge measurement and testing equipment, critical for developing technologies like MRIs. On May 16th, Keysight is hosting a free virtual event for engineers, featuring live experiments on battery performance, DC to DC conversions, and Internet of Things devices. Attendees can explore how temperature affects battery runtimes or test converter performance, with a live Q&A session to engage with experts. Registering enters participants in a giveaway for $300,000 worth of professional-grade test equipment, with extra entries for using specific sign-up links. Even if you missed the live event, recordings are available, and Keysight hosts similar events every 2 months. Whether you're an experienced engineer or new to electronics, this event offers valuable insights into the tools that make technologies like MRIs possible.